Hi, my name is Izzy Brand, and I'm excited to present our work, titled Active Learning of Abstract Plan Feasibility. Long-horizon sequential manipulation tasks, such as building a tower from blocks, can be effectively addressed by first planning in an abstract action space, which abstracts away low-level motion plans and grasps. For example, here, an abstract plan is an ordering of blocks and the relative poses between them. Once an abstract plan is found, the robot performs low-level motion planning to determine the motions and grasps it must use to achieve the desired tower. In our domain, the tower building problem is made more challenging with the addition of weights inside of the blocks, which shift the center of mass away from the center of geometry. As the robot searches over abstract plans, it must consider the feasibility of potential plans. A feasible plan is one which the robot can successfully execute in the real world. Determining the feasibility of an abstract plan with the use of a simple model, such as a physics simulator, would not accurately capture the complexity of the tower building problem. This process is subject to noise in execution and estimation. Thus, we take a learning approach. The robot is given all object properties, as well as the ability to localize, pick, and place blocks. What it must learn is how to accurately predict whether or not an abstract plan is feasible. To label a plan's feasibility, the robot must execute the plan in the real world. The process is expensive, sometimes taking up to 10 minutes to construct a single tower. Therefore, our approach must be data efficient to limit the amount of real-world experimentation needed, and autonomous to limit the amount of human intervention. In addition, a useful model is one which generalizes to multiple tasks. First, the robot performs self-guided experimentation without a specific task or goal in mind. This consists of selecting which towers to build, labeling those towers, and using the labeled data to train the feasibility model. We then evaluate our method on several downstream tasks. We first plan to achieve a task objective, and then execute that plan in the real world. During the experimentation phase, we take an information-theoretic active learning approach to minimize entropy over the feasibility model parameters. Specifically, in the selection phase, our objective is to choose plans whose execution trace would be informative about the feasibility model parameters. This approach requires a representation of model uncertainty, so we use an ensemble of graph neural networks to approximate a distribution over model parameters. The maximally informative experiment is one where each individual model in the ensemble makes a confident prediction, but the models collectively disagree. This is known as the bald acquisition function, introduced by Holsby et al., which allows information gain to be calculated in the label space instead of in the high-dimensional parameter space. We sample and score plans to find maximally informative experiments. However, since a plan execution could fail in any step, longer plans are less likely to be feasible. Additionally, when a plan fails early, we do not observe action outcomes after the plan failure. Fortunately, our learned plan feasibility model can help here. We score plans based on the expected information gain, considering the feasibility of each subplan. Having chosen the plans which are expected to be most informative, we execute those plans on the robot. An external plan success monitor supplies a label. The labeled plan executions are added to the data pool, and we retrain the ensemble of feasibility models. The robot repeats each component of the active learning loop, autonomously assembling towers and resetting the environment between experiments. In total, the robot performed 400 experiments to learn the feasibility model over the course of 55 hours. After learning a feasibility model by task-agnostic experimentation, we use the model with the Monte Carlo planner to maximize reward in multiple downstream tasks. During evaluations, we sample a set of candidate plans, and from those estimated to be feasible using our model, we select the plan that maximizes task-specific reward for execution. In this paper, we consider 3 tasks that require the robot to build challenging or unintuitive towers using blocks with shifted centers of mass. The first task is longest overhang, where the edge of the top block should be as far from the tower's base as possible. The tallest tower task simply attempts to build the tower with the greatest height. And finally, the maximum unsupported area task rewards block placements where each block has a large surface area not in contact with the block below. Here are our experimental results for predicting plan feasibility for the longest overhang task. Predicting plan feasibility with a simple physics simulator leads to many unstable towers because of unmodeled real-world noise in the system. Our learned model outperforms the physics simulation, resulting in fewer unstable towers, as it is able to capture noise in the real-world system. Unlike in simulation, collecting training data on a single real-world system cannot be accelerated or parallelized. A relatively small dataset of 400 towers took us 55 hours to execute, which is why autonomous and efficient data collection are paramount to these types of problems. We have presented an integrated robotic system which conducts self-supervised experimentation to learn abstract plan feasibility, and improves data efficiency by sampling potential plans to maximize information gain. Thank you, and please see our paper for more details.